Welcome back to yet another installment of the Ethernaut series. So today we'll be solving level 3 of Ethernaut, which is Coinflip. Let's start by getting a fresh instance of the contract. So the objective of this level is for us to guess the correct outcome of a coin flip 10 times in a row. Let's check out the actual contract itself. We will be using the flip function. Within this flip function, we can see that the result of each coin flip is actually determined by these few lines right here. As a result of each coin flip is deterministic, we can actually write a contract that pre-computes the correct guess before sending it to the flip function over here. So for this challenge, we will be using Remix. Let's start by creating a new folder called Ethernaut. Within Ethernaut, let's create a new file called flip.sol. Very nice. Let's copy the instance address of the contract. It will be useful later. Let's just paste the instance right here. So let's just copy the boilerplate for now. Right, so let's start writing our contract. Let's check out our Solidity compiler version 0.8.7. Our contract, let's just call it flip. Let's start by writing an interface because we will want to interface with this coin flip contract. So Coinflip, we will be calling the flip function. So let's just write that function. Flip takes in a bool value. Whenever you're declaring functions in an interface, they have to be marked as external. So external returns bool. Another useful function we might possibly want would be consecutive wins. I'm assuming consecutive wins is how the level of Ethernaut will be able to see if we have actually cracked this level. So let's write a view function for that. Function consecutive wins takes in no parameters. External view returns UN 256. Very nice. Next, let's incorporate our interface. So iCoinFlip private coinflip equals to iCoinFlip of the instance address of the level. What this does is that it essentially allows us to access the contract instance through our defined interface. Next, we will also need to save the factor. This will come in handy during our calculations of the coin flip outcome. Next, let's just write a function for actually flipping the coin flip contract. Function, let's just call it flip. Takes in no parameters, doesn't return anything. Let's go through the calculations of the outcome of the coin flip. So let's just repeat what the original contract did. UN block value is equal to UN of block hash block dot number -1. It is not exactly the same because the coin flip contract is using safe math and here we're not. It's not necessary here. The significance of saving block value as the last hash essentially means we can't call the flip function 10 times in a row within the same transaction because the block hash will essentially be the same. So once we have the block value, we can actually calculate the side of the coin flip. So let's just write that. Side equal to block value divided by factor is equal to 1. If the result of this calculation is equal to 1, then it returns true, else it returns false. With that in place, we can actually call Coinflip. Let's call flip on Coinflip with our guess. And that should be it. Next, for a convenience function, let's write a function that checks how many consecutive wins we have. So function check wins, takes in no inputs. It's a public function, returns a UN256. So this essentially just returns Coinflip dot consecutive wins. Very nice. What's wrong with this? You're right, it's a view function. Public view returns. Yep. So now that that is done, we can go into our injected Web3 provider, and we can deploy this contract. Fantastic. We can interact with our deployed contract right here. Let's just call check wins, assuming it's 0, it is. Let's flip the coin. Let's wait for this transaction to be mined, and then we can run check wins once more to see if we actually got it correct. Let's go check wins. Returns 1. Very nice. Let's call flip again. Guess estimation failed. So execution reverted. The transaction execution will likely fail. Usually if this appears in Remix or Hard Hat, the transaction actually will likely fail. Why this particular transaction might fail is because of this line. If last hash is equal to block value revert. So we just have to wait a bit, wait until there's a new block that is mined before calling this. Let's call this again. Let's go run check wins, and now we have 2 consecutive wins. Now all we have to do is to keep going through the motions until consecutive wins is equal to 10. So I just finished the 10th flip of the Coinflip contract. Let's go check wins. 10. Very nice. Assuming everything is passed, we should then be able to simply submit the contract instance and get this W. I think the main point of this challenge is to showcase that true randomness is simply inaccessible within the EVM. To get cryptographically proven random numbers, we should be using Chainlink, an Oracle solution that can provide us with verifiable random numbers. So that's it for this video. Stay tuned for more Ethernaut content.